Hello, everyone, and welcome. I'm excited to have you here today. We're about to dive into the world of programming with a focus on Python. The slide you're seeing now is our introduction to Python programming. In this session, we'll explore what Python is, why it's so popular, and how you can start using it effectively. We'll touch on basic concepts, practical applications, and some tips to get you started. But for now, let's keep it brief and get ready to explore the fascinating world of Python together. Let's begin by understanding what this slide covers. We are looking at slide 2 out of 58, which focuses on the foundational aspects of Python. This slide lists several key topics that are essential to grasp as we explore Python programming. First, we see Unit 1 Introduction to Python. This indicates that we're starting with the basics, setting the stage for everything else. It's important because it helps us understand what Python is and why it's so popular today. Next, Learning Outcome highlights what you should expect to learn from this section. It sets the tone and goals for your learning journey. Moving to Characteristics of Computer Program. This reminds us that understanding what makes a good program is vital. Things like clarity, efficiency, and correctness. Then, what is Python? Clarifies the core question. Python is a high-level, interpreted language known for its simplicity and versatility. Following that, Python is open source, emphasizes that Python's source code is freely available. This openness fosters a large community, continuous improvement, and plenty of resources for learners and developers alike. We then see Features of Python, which include things like easy syntax, dynamic typing, and extensive libraries, features that make Python user-friendly and powerful. Object-oriented programming is another key concept, highlighting Python's support for OOP principles such as encapsulation, inheritance, and polymorphism. This paradigm helps us write modular and reusable code. Programming errors points to the common mistakes we might encounter, like syntax errors or logical bugs, and how understanding these helps us write better code. Finally, Role of PVM refers to the Python virtual machine, which executes Python code. It's a crucial component because it interprets your scripts into actions that the computer can perform. Overall, this slide sets the foundation, covering what Python is, its features, paradigms, and the environment in which it runs, giving you a comprehensive starting point for your Python learning journey. Today, we'll focus on understanding the basics of Python programming constructs. This is fundamental because these constructs are the building blocks for writing effective and efficient code. By the end of this course, a student who successfully completes it will have the ability to explain key concepts clearly and thoroughly. We want you to grasp how these elements work together and why they are important. Remember, mastering these basics is essential for connecting to more advanced topics later on. So, let's dive into the core ideas that will set a solid foundation for your Python programming journey. Today, we'll explore some fundamental aspects of Python that form the backbone of programming in this language. We'll start with a brief history, understanding how Python evolved and why it became so popular. Then, we'll look at its key features, such as simplicity, readability, and versatility, which make it accessible for beginners yet powerful enough for experts. Next, we'll discuss how to execute a Python program, highlighting the different ways to run Python code, whether through IDEs, command line interfaces, or notebooks. We'll also explore the various flavors of Python, including CPython, Jython, IronPython, and others, each tailored for specific environments or purposes. We'll touch on the importance of comments in code, which help us document our logic and make our programs understandable. Then, we'll move into data types, covering built-in data types like integers, floats, strings, and booleans, and how they form the building blocks of our programs. Sequences are crucial too. They allow us to handle ordered collections of data, such as lists, tuples, and strings. Understanding literals, which are the raw data values, and operators, which perform operations on data, is essential for constructing meaningful expressions. We'll also look at input and output statements, how to interact with users and display results. Conditional statements along with loops like for and while, give our programs control flow, enabling us to perform repetitive tasks efficiently. Alongside these, commands like break, continue, pass, and assert help us manage loop execution and error handling effectively. Finally, we'll see how the return statement allows functions to send results back to the caller, completing the cycle of defining and executing reusable blocks of code. All these concepts come together to give you a solid foundation in Python programming, connecting to the broader theme of building robust and efficient software solutions. Let's talk about what a computer program actually is. Essentially, it's a collection of instructions designed to perform a specific task. When we run these instructions on a computer, they guide the machine to do what we want. Think of it as giving the computer a set of step-by-step directions. Now, for a computer to do anything meaningful, it needs these programs. Without them, the hardware, like the processor, would just be idle. The computer's central processing unit, or CPU, is where all the action happens. It executes the instructions from the program, following them to carry out tasks efficiently. This connection between instructions and execution is fundamental. It's what transforms raw hardware into a powerful tool that can do everything from simple calculations to complex operations. So, understanding programs is key to understanding how computers work and how we can make them serve our needs. Now, let's talk about some key characteristics of a good computer program. First, platform independence is crucial. This means that a well-designed program can run on a variety of systems without needing major modifications. It's all about portability, making sure the software can be used across different environments seamlessly. Next, self-explanatory features are vital. A program should be easy to understand and use, reducing the need for extensive documentation or training. This enhances user experience and efficiency. Handling unexpected errors is another critical aspect. Good programs can detect errors as they happen and provide proper messages, guiding users on what went wrong and how to fix it. This reliability builds trust and prevents frustration. Reliability itself is fundamental. Users need to depend on the program to perform consistently and correctly over time. Communication also plays a role here. Clear, effective communication within the program, like informative messages, helps users stay informed and feel confident while navigating the software. A friendly user interface ties all these qualities together. When a program is easy and pleasant to interact with, it encourages user engagement and satisfaction. Finally, efficiency is key. A good program executes tasks faster and uses minimal memory, which improves overall performance and resource management. So in essence, these characteristics, portability, clarity, robustness, effective communication, user-friendliness, and efficiency, are the building blocks of a high-quality computer program that meets user needs and stands the test of time. Let's take a closer look at some common programming errors. When a program is executed, sometimes it runs into issues that prevent it from working correctly. One of these is a runtime error, which happens while the program is running. For example, trying to divide by 0 or accessing an invalid memory location can cause such errors. Next, we have errors related to the meaning of the code, known as semantic errors. These occur when the syntax is correct, but the logic or the intent behind the code is flawed. For instance, using a variable in a way that doesn't make sense for what you're trying to achieve. Then there are syntax errors, which are issues with the structure of the program itself. These happen when the code doesn't follow the rules of the programming language, like missing a semicolon or misplacing parentheses. Syntax errors are usually caught early, often during compilation or parsing. Understanding these different types of errors helps you troubleshoot more effectively. Recognizing whether an error is syntactical, semantic, or a runtime issue guides you in fixing it faster and writing more reliable code. Let's start by looking at examples of different types of languages. When we consider programming languages, they are all designed to be clear and precise, which makes them unambiguous in nature. They tend to be less redundant, meaning they don't repeat information unnecessarily, and they are very close to actual computer code, which helps machines interpret them accurately. For example, languages like French, English, and German serve as examples of natural languages. These are used for specific applications and are much closer to how humans communicate. Now, on the other hand, when we talk about formal languages, such as FL, they tend to be more ambiguous and contain more redundancy. This is because they are often spoken by people and are geared toward human understanding, which naturally involves some level of ambiguity and repetition. Moving to natural language, or NL, this is the language we use every day, spoken, written, and full of nuance. It's inherently more flexible and expressive, but also more complex to interpret computationally. That's why understanding the differences between natural language and formal language is crucial in areas like natural language processing, as it helps us bridge the gap between human communication and machine understanding. All right, let's talk about the different programming paradigms. On this slide, we see there are two main types: object-oriented programming and procedural programming. Procedural programming is a style where we focus on a sequence of instructions or procedures to perform tasks. It's straightforward and easy to follow, especially for simple programs. On the other hand, object-oriented programming organizes code around objects, which are instances of classes that encapsulate data and behavior. This approach makes it easier to manage complex systems, promote code reuse, and improve maintainability. Understanding these paradigms is essential because they influence how we design and structure our programs. Depending on the project's requirements, we might choose one paradigm over the other to optimize development and future scalability. These are foundational concepts that underpin many modern programming languages and techniques. Let's talk about procedural programming, which is a fundamental programming paradigm. In this approach, data and the operations performed on that data are kept separate. That means, when you're writing code, you focus on functions or procedures that manipulate data, but the data itself is often just accessible directly. One of the key points here is that it doesn't support data hiding or encapsulation, which are important concepts in modern object-oriented programming. This means that data can be accessed and modified from anywhere in the program, which can sometimes lead to less control over data integrity. Procedural programming typically follows a top-down approach, where you start with high-level procedures and break them down into smaller sub-procedures. This makes the flow of the program easier to understand from a logical perspective. Another important aspect is that global data sharing is allowed. This means that variables can be accessible across different parts of the program, which simplifies data sharing, but can also introduce risks if not managed carefully. Languages like C and Pascal are classic examples of procedural programming languages. They show how procedures and functions are central to program structure, emphasizing a step-by-step, linear execution flow. Overall, while procedural programming is straightforward and easy to grasp, especially for beginners, it has limitations when it comes to data security and modularity. That's why modern programming often combines this approach with others to build more robust and maintainable software. Let's talk about the bottom-up approach. This method supports important principles like data hiding and encapsulation, which are essential for creating secure and well-structured programs. With this approach, data can be easily moved between methods, and you can control access to that data through access specifiers. This control helps prevent unintended interference and maintains integrity. Examples of languages that use this approach include Java and C++. Interestingly, Python is a bit of a hybrid. It supports both procedure-oriented programming and object-oriented programming, giving developers flexibility. Understanding this approach helps us see how different programming languages implement OOP principles effectively. Python is a great language for beginner-level programmers because it's easy to learn and supports the development of a wide range of applications. From simple text processing to creating web browsers or even games, Python can handle it all. One of the reasons it's so beginner-friendly is that you can actually sit at a Python prompt and interact directly with the interpreter to write your programs. This makes experimentation and learning much more straightforward, as you see immediate results. Python also supports object-oriented programming, which means you can encapsulate code within objects, making your programs more organized and reusable. Another key point is that Python is processed at runtime by the interpreter, so you don't need to compile your code before running it, much like Perl and PHP. This interpreted nature allows for quick testing and development. Overall, Python is a high-level, interpreted, interactive, and object-oriented scripting language. It's designed to be highly readable, using English keywords more often than punctuation, which makes it easier to understand. It also has fewer syntactical rules compared to other languages, helping new programmers get started quickly. Python was conceived in the late 1980s, a period of rapid growth and innovation in programming languages. It was developed in 1989 by Guido van Rossum, who was working at the Centrum Wiskunde en Informatica, or CWI, in the Netherlands. Guido aimed to create a successor to the ABC programming language, which was known for its simplicity and readability. One of the key features he wanted to include was exception handling, to make programs more robust and easier to debug. He also wanted Python to interface smoothly with the Amoeba operating system, which was quite advanced for its time. The first version of Python, 0.90, was released in February of 1991, marking the beginning of what would become a hugely influential language in the tech world. This history underscores Python's roots in making programming more accessible and powerful, aligning perfectly with our overall theme of innovation and usability in technology. Let's take a look at the release timeline for Python, starting with Python 1, which was released back in January 1994, marking the beginning of its journey. Moving forward, Python 1.5 was released at the end of 1997, showing steady development. Then, in October 2000, Python 2 came out, introducing important features that shaped future versions. Following that, we see a series of releases in the 2000s, with Python 2.4 in late 2004, Python 2.5 in 2006, and Python 2.6 in 2008. Notably, Python 2.7 was released in July 2010 and became a long-standing version used by many projects for years. In terms of Python 3, the major version shift from 2 to 3 happened with Python 3 in December 2008, which introduced significant changes. Since then, we've had multiple Python 3x releases, such as Python 3.1 in 2009, 3.2 in 2011, 3.3 in 2012, 3.4 in 2014, 3.5 in 2015, and most recently, Python 3.6 in December 2016. These dates highlight how Python has evolved over more than 2 decades, continuously adding features and improving performance. This timeline not only shows the growth of the language, but also reflects its increasing popularity and stability in various applications. Understanding these milestones helps us appreciate the maturity of Python today and the foundation for future development. Let's take a closer look at some of the key features that make Python such a versatile and powerful language. First, Python provides interfaces to all major commercial databases, which means you can easily connect and work with different database systems within your Python programs. This is crucial for data-driven applications. Next, a lot of Python's standard library is designed to be very portable and cross-platform compatible. Whether you're working on Unix, Windows, or Macintosh, your code can run smoothly without needing major changes. This portability makes Python a great choice for diverse development environments. Another important point is that Python is extendable. You can add low-level modules to the interpreter, allowing programmers to customize and enhance their tools as needed. This flexibility opens up many possibilities for optimization and specialized functionality. Compared to shell scripting, Python offers a better structure and support for large programs. Its source code is fairly easy to maintain, which is essential as projects grow in complexity. Clear, organized code helps teams collaborate more effectively and reduces bugs. When it comes to GUI programming, Python supports creating GUI applications that can be ported across many systems, including Windows, Macintosh, and Unix. This cross-platform capability simplifies the development process for user interfaces. Python also runs on a wide variety of hardware platforms, maintaining the same interface across all of them. This portability ensures that your code can be deployed in many different environments without hassle. Another significant feature is that Python code is very easy to read. Its clear syntax and minimal keywords make it accessible, especially for beginners, and enhance overall readability for seasoned developers. Python includes an interactive mode, which is extremely useful for testing and debugging snippets of code instantly. This interactivity accelerates development and helps in quickly identifying issues. Finally, Python's simple structure and well-defined syntax mean that it's easy to learn. Students and new programmers can pick up the language quickly, making it an excellent choice for education and rapid development. All these features collectively highlight why Python is such a popular and effective programming language for a wide range of applications. When we write Python code, it doesn't run directly on the hardware. Instead, the code is first compiled into what's called bytecode, which is a sort of intermediate language. This bytecode is stored in a file with a pic extension. For example, if you have a file named program, after compilation, it becomes program, pic. This bytecode is then fed into the Python virtual machine, or PVM, which interprets it. The PVM reads the bytecode and executes the instructions to produce the desired output. One of the great things about Python is that this entire process, compiling to bytecode and then executing, happens automatically behind the scenes. As users, we don't need to worry about these steps. Python takes care of it all seamlessly. This automation helps make Python both powerful and user-friendly, aligning with its goal of simplicity and ease of use. When Python runs on a computer, the behavior it exhibits regarding bytecode depends on the access permissions. If Python does not have write access, it generates the bytecode and temporarily stores it in memory. This stored bytecode is discarded once the program exits, meaning it doesn't save any of this data permanently. However, if Python has write access on the computer, it takes a different approach. It actually stores the bytecode in a file with a pic extension. This is quite useful because saving the bytecode helps speed up the startup process for subsequent runs. The next time you run the program, Python checks for this pic file. If it finds it and the source code hasn't changed, it loads the bytecode directly from the file. This allows Python to skip the compilation step, making the program start faster. Understanding this behavior is important because it highlights how Python optimizes performance by caching bytecode, especially when you have write access. It's a key part of Python's efficiency, helping reduce load times and improve overall execution speed. Python is a programming language that uniquely combines features from both C and Java. It offers the elegant style of developing programs similar to C, making code more readable and concise. At the same time, Python provides object-oriented capabilities like Java, with support for classes and objects that enable us to organize code more effectively. This blend of features makes Python a versatile language, suitable for a wide range of applications. Understanding these key points helps us see why Python is such a popular choice in the programming world. It seamlessly integrates the best aspects of different languages, aligning perfectly with our overall theme of exploring powerful and flexible programming tools. The name Python actually comes from the famous TV show Monty Python's Flying Circus. It's a fun story because many people assume it's related to the snake, but it's really a nod to that British comedy series. Now, moving on to the code example here, a b equals 10. This line is a quick way to assign the value 10 to both variables a and b at the same time. It's a handy shortcut in programming. Then we have the print statement, print, sum equals, a plus b. This line outputs the sum of a and b, which is 20 in this case. It's a simple example, but it really highlights how we can do basic arithmetic and display results. Overall, this example ties into our theme of understanding how Python makes programming straightforward and accessible, even for basic operations like adding two numbers. Python is open-source software, which means that anyone can download it from the official website at www.python.org. This openness allows developers from all around the world to access the source code freely. Because of this, they can use Python to develop their own programs, customize it to fit their needs, or contribute improvements back to the community. This collaborative approach not only accelerates innovation, but also ensures that Python remains flexible and constantly evolving. It's a core reason why Python has become so popular and widely adopted across different industries. So, when we say Python is open source, we're emphasizing its accessibility and the vibrant community that supports its growth. This openness really ties into the overall theme of how accessible and versatile Python is as a programming language. Now, let's take a closer look at some of the different flavors of Python. As you can see on the slide, there are several variants like Anaconda Python, PyThunkC, Stackless Python, Ruby Python, PyPy, Iron Python, Jython, and CPython. Each of these is used to include various programming languages into Python, or to provide specific features tailored to different needs. The key idea here is that these are different types of Python compilers or implementations, often called flavors. They serve different purposes depending on what you're trying to achieve, whether it's performance optimization, integration with other languages, or specific platform compatibility. For example, CPython is the default and most widely used implementation. Others like IronPython and Jython are designed to run on .NET and Java platforms, respectively. PyPy focuses on speed through just-in-time compilation, while Anaconda Python is a popular distribution that simplifies package management for data science. Understanding these flavors helps us see the flexibility of Python and how it can be adapted to various environments and requirements. This diversity is part of what makes Python such a versatile programming language across different fields and projects. Now, let's take a closer look at the standard Python implementation in C essentially. What happens here is that any Python program you write is first converted into bytecode using C language functions. This bytecode isn't just stored. It's executed on an interpreter that runs within the Python virtual machine, or PVM, which itself is created in C. This setup allows Python to be both flexible and powerful, because it can execute C and C++ functions and programs directly. This integration is one of the reasons Python is so versatile and widely used. It's essentially bridging high-level scripting with the power of lower-level languages, all within a C-based environment. This underpins the core of CPython, which is the most common implementation of Python, and it's what makes Python both accessible and efficient at the same time. Now, let's take a closer look at Jython, which is also known as JPython. It's designed specifically to run on the Java platform. What makes Jython interesting is that it allows Python code to work seamlessly with Java. The way it works is that, first, the compiler takes your Python program and compiles it into Java bytecode. Then, this bytecode is executed by the Java Virtual Machine, or JVM. This process bridges the gap between Python and Java, making it easier for programmers to leverage the strengths of both languages. Libraries are a big part of this as well, since they can be useful for both Python and Java programmers, helping to share resources and tools across both communities. If you're interested in learning more or trying it out, you can visit www.jython.org. Overall, Jython exemplifies how interoperability can open up new possibilities for developers working within the Java ecosystem. IronPython is designed specifically for the .NET framework, which means it integrates seamlessly with the Microsoft ecosystem. It's written in C#, a language many developers are familiar with, making it easier to work within this environment. When you compile IronPython code, it generates intermediate language, or IL, which runs on the Common Language Runtime, or CLR. This process allows your Python code to leverage the power and performance of Net. One of the most exciting aspects of IronPython is its flexibility. It enables you to use both Net libraries and Python libraries within a single project. This hybrid approach opens up a lot of possibilities for building versatile applications. If you're interested in exploring more, you can visit their website at www.ironpython.net. Overall, IronPython exemplifies how you can bring together different programming worlds to create more dynamic and powerful solutions. Let's take a closer look at PyPy. Essentially, it's an implementation of Python written in RPython, which itself was created using Python. This layered approach is quite interesting because RPython is specifically designed to help create efficient language interpreters. Now, what makes PyPy stand out is its speed. Since it includes a just-in-time, or JIT, compiler along with the PVM, or Python virtual machine, programs run much faster than with standard Python. This combination allows for dynamic optimization during runtime, significantly boosting performance. So, when you're working with PyPy, you're leveraging both the flexibility of Python and the efficiency of JIT compilation, making it a powerful tool for high-performance applications. For more information, you can visit pypy.org. Now, let's take a look at how Ruby and Python can work together seamlessly through a bridge. This slide introduces RubyPython, a tool that essentially encloses the Python interpreter inside Ruby applications. What this means is that you can run Python code directly from your Ruby environment, which opens up a lot of possibilities for integrating libraries and functionalities from both languages. It's like creating a bridge that allows these two powerful tools to communicate and collaborate. If you're interested in exploring this further, you can find more information at RubyPython.org. This integration exemplifies the broader theme of interoperability in programming, showing how different languages can work together to enhance your projects. Let's talk about creating threads and tasklets in stackless Python, which is a re-implementation of the original Python. You can find it at pypy.org/pypy/stacklesspython/10.0. If you're familiar with traditional Python, you'll notice that stackless Python introduces a different way to handle concurrency. Small tasks that are meant to run independently are called tasklets. These tasklets are lightweight, and they run on the CPU independently, allowing for efficient multitasking. They communicate with each other through channels, which act like managers. Channels handle scheduling, control, and suspension of tasklets, making it easier to coordinate complex workflows. A thread in this context is a process that can run hundreds of these tasklets simultaneously. This approach provides a more scalable and flexible way to manage concurrent operations, especially when compared to standard threading models. Overall, stackless Python's design focuses on making concurrency more manageable and efficient, which aligns perfectly with our theme of optimizing performance and simplifying complex programming tasks. Let's talk about Python XY, which is pronounced as Python XY and written as Python in parentheses with X and Y as parameters. This version is specifically tailored for scientific and engineering-related packages, making it a powerful tool for technical computing. If you're interested, you can find more information and download options at Python XY, GitHub.io/downloads, HTML. It's a great resource for anyone working in data analysis, simulation, or engineering fields who needs a robust Python environment pre-configured with essential tools. Let's talk about handling large-scale data processing, predictive analytics, and scientific computing, which is where Anaconda Python really shines. It's a powerful distribution that's specifically designed to focus on working with big data, making complex analyses more manageable. When you're dealing with vast amounts of data or sophisticated models, Anaconda provides the tools and environment you need to get the job done efficiently. If you're interested in exploring or downloading it, you can visit www.continuum.io/downloads. This tool is a cornerstone for anyone looking to scale their data science and analytics projects effectively. Now let's talk about the PVM, or Python virtual machine. Essentially, it converts any program into machine code before the computer actually executes it. This step is crucial because it allows Python to be flexible and platform independent. Typically, a compiler takes your source code and translates it directly into machine code that your computer's processor can understand. But in Python's case, instead of direct compilation, the code is first converted into bytecode. This bytecode acts as an intermediate, which the PVM then interprets or executes. This process helps Python maintain its high level of portability and ease of use. So, to connect this to the overall theme, understanding how the PVM works gives us insight into why Python is so versatile. It's all about how the code is transformed and executed behind the scenes. Bytecode is a fixed set of instructions that Python developers create to represent all kinds of operations. Each of these instructions takes up exactly 1 byte, which makes it efficient and easy for the computer to process. It's important to note that Python's organization allows for new instructions to be added over time, so the bytecode can evolve as the language develops. When Python compiles your code, it stores this bytecode in a file with a PIC extension. This file is what the Python virtual machine, or PVM, uses to run your program efficiently. So, understanding bytecode helps us see how Python translates our high-level code into a form that the computer can execute quickly and effectively. Now, let's delve into how the PVM handles bytecode instructions. Essentially, the PVM converts these instructions into machine code so that the computer can understand and execute them. To do this, the PVM is equipped with an interpreter, which plays a crucial role here. The interpreter takes the bytecode and translates it into machine code on the fly. Because of this real-time translation process, we refer to the PVM as an interpreter. This mechanism allows Python code to run across different platforms without needing to compile it into machine code ahead of time, making the PVM a flexible and powerful component in Python's execution model. Let's take a closer look at the comparison between C and Python. First, C is a procedure-oriented language, which means it focuses on functions and procedures to perform tasks. It doesn't natively support features like classes or objects, which are fundamental in object-oriented programming. On the other hand, Python is also procedure-oriented, but includes powerful object-oriented features such as classes and objects, making it more flexible for various programming paradigms. When it comes to execution speed, C generally runs faster than Python because it is a lower-level language that compiles directly to machine code. Python, being an interpreted language, tends to be slower in comparison. In C, you need to declare data types for variables and arrays explicitly, which enforces type discipline but requires more upfront planning. Python, however, doesn't require explicit type declarations. It uses dynamic typing, which makes coding more flexible and quicker to write. Speaking of type discipline, C has static and weak typing, meaning types are checked at compile time, but the language allows some implicit conversions that can lead to errors. Python has strong and dynamic typing, so types are checked at runtime, and type errors are caught during execution, offering more safety. Pointers are a core feature in C, enabling direct memory manipulation, which is powerful but can also introduce complexity and bugs. Python does not use pointers directly, abstracting away memory management to simplify programming. C lacks built-in exception handling, so error management often requires manual checks and handling. Python, however, provides a robust exception handling mechanism, making it easier to write reliable and maintainable code. Regarding control structures, both languages support loops like while and for. C also has a switch statement for multi-way branching, but Python does not have a switch statement, though similar functionality can be achieved using if-else chains. Finally, in C, the variable in a for loop doesn't increment automatically. You need to specify the increment explicitly. In Python, the for loop automatically handles the loop variable's progression, which often makes code cleaner and easier to read. Overall, these differences highlight how C is more low-level and performance-oriented, while Python emphasizes simplicity, flexibility, and ease of use, aligning with different programming needs and project requirements. So let's take a moment to compare C and Python in terms of memory management. In C, you need to manually allocate and deallocate memory using functions like malloc and calloc. This means you have to be very careful about managing memory yourself, which can be powerful but also prone to errors like leaks. On the other hand, Python handles memory automatically through its built-in virtual machine, PVM. This means you don't have to worry about explicitly freeing memory. Python takes care of it for you, making development easier and less error-prone. Another key difference is garbage collection. C doesn't have a garbage collector, so you need to handle all memory cleanup manually. Python, however, includes an automatic garbage collector, which helps free up memory that's no longer in use without any extra effort on your part. Finally, syntax-wise, C requires a semicolon at the end of each statement, which is a strict syntax rule. In Python, there's no need for semicolons. The language relies on indentation and line breaks to define code blocks, making the code cleaner and often easier to read. So, in summary, Python's automatic memory management and simpler syntax can make coding more straightforward, especially compared to C's manual approach. Now, moving on to slide 35, which focuses on the diverse ecosystem of Python libraries. As you can see, there's a wide range of tools available that cater to different needs. For example, Whoosh is a powerful library for indexing and searching, making it ideal for building search functionalities. Then we have SciPy, which is essential for scientific and engineering computations, offering advanced mathematical functions. NumPy is fundamental for handling single and multi-dimensional arrays, providing the backbone for numerical processing. Cryptography libraries enhance security by enabling encryption and decryption, while W3lib offers web-related utilities. PyQuery allows us to work with HTML documents in a way similar to jQuery, which makes web scraping more intuitive. SUMPy, which is focused on algebra, provides the mathematical operations needed for symbolic computations. When it comes to databases, MySQL Connector Python makes connecting and interacting with MySQL databases straightforward. On the web development side, Cherapy is an object-oriented HTTP framework that simplifies building web applications. Sphinx is our go-to tool for generating documentation, and Pillow is widely used for image processing. Jellyfish helps with string comparisons and phonetic algorithms, which can be useful in data cleaning tasks. Pandas is indispensable for data manipulation and analysis with its robust data structures. Bodo allows seamless interaction with Amazon Web Services, and Fiona provides tools for working with big data files, especially geospatial data. Finally, argparse is a command-line parsing library that makes it easy to create user-friendly command-line interfaces. Altogether, these libraries highlight how rich and versatile the Python ecosystem is, enabling us to tackle a broad spectrum of projects efficiently. This diversity is what makes Python such a powerful language for developers across different domains. Now, let's look at a practical example of running Python code directly from the command line. When you see the command C, Python, disprogram, Py, what we're doing is instructing Python to disassemble the bytecode of the specified program. The mdis part tells Python to use the disassembler module, which is really useful for understanding how your code is translated into lower-level instructions. This can be especially helpful for debugging or optimizing your code. So, by executing this command, you're essentially peeking under the hood to see what the Python interpreter is doing with your script. It highlights the importance of understanding how Python executes code, which ties back to our overall theme of gaining deeper insights into the language's inner workings. So here we see that some memory is allocated with the name, and it holds the value 1. Essentially, when we write a equals 1 in Python, what's happening behind the scenes is that Python creates a memory space, labels it with the name, and stores the value 1 there. Think of a variable like a storage box. By giving it a name, we can easily reference and manipulate the data stored inside. This example helps illustrate how Python manages variables. Each variable is linked to a specific memory location, which makes our code more flexible and easier to work with. Remember, understanding this connection between variable names and memory is fundamental to grasping how Python handles data internally. Now, let's look at this simple example where a equals 2. If we change the value of the variable, in this case to a different number, then the box in our visualization will update accordingly with that new value. This demonstrates how variable updates work dynamically. Anytime we modify a variable, everything that depends on it, like this box, will reflect the change immediately. It's a fundamental concept because it shows how changing data can instantly influence what we see or compute, making our programs more interactive and responsive. This idea ties back to our overall theme of understanding how variables drive the behavior of our applications. Let's look at this example. The value 1 is created first in memory, and then a tag is created. So when I write a equals 1, I'm assigning the value 1 to the variable a remember. A variable isn't just a container. It's actually a tag or a name that's tied to a specific value. In Python, this concept is fundamental because it shows how variables work behind the scenes. They act as labels attached to data, making it easier to work with complex programs. Understanding this helps us see how Python manages data efficiently and how variables are more than just placeholders. They are references to actual data stored in memory. Python has tags to represent values. Only one memory is referenced by two names. Python is using memory efficiently. Now, let's talk about comments in Python. As you can see, there are two main types. First, we have multi-line comments, which are useful when you want to add more detailed explanations or notes within your code. For example, you might write something like this, spanning multiple lines to clarify complex sections. These are especially helpful for making your code more understandable for others or even for yourself when you revisit it later. Then there are single-line comments, which are simpler and are typically used for brief notes or explanations. They start with a hash symbol or slash number in some cases, and everything after that on the same line is considered a comment. The key points to remember are that comments can prevent code from executing, which is useful during testing or debugging, and that they play a vital role in making your code more readable and maintainable. As we continue, keep in mind how these comments help you and others understand what your code is doing without needing to decipher every line. Let's begin by opening Python's GUI. To do this, simply press the Start button on your computer, then type Python into the search box. From the list of results, select Idle Python GUI. This is the integrated development environment that allows us to write and run Python code easily. It's a crucial first step because it provides a user-friendly interface, especially for beginners. By opening this Python shell prompt, we're setting ourselves up to start coding right away. Remember, familiarizing yourself with this environment will make your learning process much smoother and more enjoyable. So, go ahead and open it now, and we'll continue from there. Let's take a closer look at the different running modes for Python. First, you can press the F5 key to run your script, which is a quick way to execute your code. When it comes to the extension of a Python script, it's always. That's the standard file extension that indicates a Python program. Now, there are two main modes in which you can run your Python scripts. The first is script mode, which is used when you're writing and executing your Python files directly. The second is interpreter mode, also known as conversation mode, which is called idle. Idle is a simple integrated development environment that allows you to run Python commands interactively. Understanding these modes is important because they impact how you develop and test your code. Script mode is great for running entire programs, while idle's interpreter mode is perfect for testing small snippets or experimenting with code on the fly. Recognizing when to use each mode helps streamline your workflow and makes your programming experience more efficient. So, in summary, knowing how and where to run your Python scripts, whether through F5, in script mode, or in idle's interpreter mode, is key to mastering the development process and ultimately becoming more productive as a programmer. IDLE is an integrated development environment, or IDE, specifically designed for Python programming. It's most commonly used on Windows systems. What makes idle really user-friendly is its multi-window text editor, which allows you to write and edit your code efficiently. It also has syntax highlighting, so keywords and functions are color-coded, making your code easier to read and debug. Auto-completion is another handy feature that suggests code completions as you type, saving you time and reducing errors. The Smart Indent feature helps keep your code properly formatted, which is crucial for Python's syntax. Beyond just editing code, idle provides a Python shell that also uses syntax highlighting, giving you immediate feedback and interaction with your code. Plus, it includes an integrated debugger, which lets you step through your code line by line, set breakpoints that persist across sessions, and identify issues more effectively. Overall, idle combines these tools to create a streamlined environment that supports both learning and developing in Python, fitting perfectly into our theme of accessible, user-friendly coding environments. Let's take a closer look at some basic Python expressions and how they work. First, we see the line with "Hello World" inside quotes, followed by "Hello World" also in quotes. This demonstrates how Python treats text as strings, which are sequences of characters enclosed in quotes. When we see the print statement, like print "Hello World," it outputs the text inside the quotes to the screen. Next, notice the expression 3 plus 7, which results in 10. This highlights how Python performs arithmetic operations directly. Moving on, the comparison 3:15 evaluates to true, showing how Python can compare values and return Boolean results, which are fundamental for decision-making in programs. Finally, we see a print statement with printme, which outputs the string inside the quotes. But then, there's printme without quotes, which attempts to print a variable named me. If me hasn't been defined elsewhere, this would cause an error. Overall, this slide emphasizes how Python handles strings, performs calculations, and evaluates comparisons, all essential pieces of the language's core functionality as we continue exploring programming concepts. Let's take a look at some examples of the print statement in Python. First, when we write print hello, with single quotes around hello, it simply outputs hello. Next, if we add a comma after the string, like print hello, it prints hello but does not move to a new line. Now, if we include multiple items separated by commas, such as print hello, there, it prints hello and there with a space between them. Moving on, we see that using double quotes, as in print hello world, works just the same, outputting hello world. Lastly, triple quotes like print hello world also output the text inside them, which is useful for multi-line strings, but here it just prints hello world. The key points to remember are that quotes can be single, double, or triple, and that a comma at the end of the statement prevents moving to a new line. When multiple elements are separated by commas, Python prints them with a space in between. Understanding these nuances helps you control exactly how your output appears, which ties into the overall theme of mastering Python syntax and output formatting. All right, let's talk about data types. When we store data in a variable or in memory, the type of data we're working with is really important. It determines what kind of information the variable can hold and how that information is processed. There are two main categories to keep in mind: built-in data types and user-defined data types. Built-in data types are provided by the programming language itself, like integers, floating point numbers, characters, and booleans. These are the basic building blocks that we use most of the time. On the other hand, user-defined data types are created by us, the programmers, when we need more complex or specific data structures that aren't covered by the built-in types. Understanding these data types helps us write more efficient and effective code, and it ties back into the overall theme of how we manage and organize data in programming. Now, let's take a closer look at some of the fundamental built-in data types in Python. First, we have sets, which are collections of unique elements, great for when you need to eliminate duplicates or perform mathematical set operations. Moving on, we have numeric types, including integers, floats, and complex numbers, which allow us to perform mathematical calculations with precision. Then there are mappings, with dictionaries being the most common example, and these are key-value pairs that help us organize data efficiently. Sequences are another essential type, encompassing lists, tuples, and strings. These are ordered collections that we can access via indices. We also have the none type, which is used to represent the absence of a value, kind of like a placeholder. Overall, these 5 types form the core of Python's data handling capabilities, enabling us to write flexible, efficient, and readable code. Let's talk about objects that don't hold any value, similar to Java's null. In Python, we have a single object called none. It's used mainly as a default value in function arguments. So when you define a function and don't pass a specific value, Python assigns none by default. And an important point to remember is that in Boolean contexts, none is treated as false. This makes none a very useful placeholder when you need to indicate the absence of a value, and it plays a key role in controlling flow and logic in your programs. All right, let's talk about numeric types. When we deal with numbers in programming, we mainly have 3 types: float, int, and complex. Float stands for floating point numbers, which are used for decimals or real numbers. Int is short for integers, so whole numbers without any fractional part. Then we have complex numbers, which include a real part and an imaginary part, and they're especially useful in scientific calculations. These numeric types are fundamental because they let us perform calculations, store data, and manipulate numbers in various ways. Understanding these subtypes helps us choose the right type for the task at hand, ensuring our programs are both efficient and accurate. So, knowing the differences and uses of float, int, and complex is key to mastering numerical computations in programming. All right, let's look at this example. We assign the value 20 to x with x equals 20. Then, when we print x, it displays 20 on the screen. This is straightforward because x is holding a number. Next, we use the type function to see what kind of data is. When we print type of x, it tells us that is an integer, which is a whole number without any decimal point. In this case, 48 is just another example of an integer. Recognizing data types like integers is crucial because it helps us understand how Python treats different values, especially when performing calculations or functions. Remember, integers are a fundamental data type in programming, and knowing how to identify them is essential as we build more complex programs. All right, let's look at this example. Equals float of 20.5. What we're doing here is converting the number 20.5 into a floating point number, which is a type used to represent decimal values in Python. When we print x, it displays the value as a floating point number. This concept is important because floating point numbers, or floats, can contain decimal points, making them essential for calculations requiring precision, like measurements or financial data. Remember, using float allows us to work with real numbers, not just integers. This example ties into our overall discussion about data types in Python, highlighting how and why we use floats to handle decimal values effectively. Let's look at how to create and display a complex number in Python. When we write x equals complex, 1j, we're defining a complex number where the imaginary part is 1. Then, by using print x, we can see the value of that complex number. A complex number in Python is written in the form of a plus bj or a plus bj in this notation. A is the real part, and b is the imaginary part. For example, if we have 3 plus 4j, the real part is 3, and the imaginary part is 4. Understanding complex numbers is important because they play a key role in many areas like engineering, signal processing, and scientific computations. In Python, working with complex types is straightforward, and this slide shows how we can define and display them easily. So remember, the key points here are the syntax for creating complex numbers and how Python represents them when printed. This will be a foundation for more advanced numerical work you'll see later in the presentation. Let's talk about how different number systems are represented in programming. When working with octal numbers, you'll see a prefix of 00 or 00 before the number. For example, 00755. This helps distinguish octal from other systems. Moving on to hexadecimal values, these are prefixed with 0x or 0x, like 0xFF, which is common in color codes or memory addresses. Then, for binary numbers, the prefix is 0b or 0b, such as 0b11011. Recognizing these prefixes is key because they tell us what number system we're dealing with, which is essential for understanding how data is represented and manipulated in different contexts. This concept ties into the overall theme of how computers process various types of data efficiently. Let's talk about converting numbers into different systems. First, we have the convert number into hexadecimal, which is often used in computing for representing memory addresses. In Python, you can do this with the hex function. For example, if you want to convert the number 3 into hexadecimal, you simply call hex 3, and it will give you the hexadecimal string. Next, there's converting a number into octal, which is another base system used in programming, especially for permissions in Unix-like systems. You can do this with the oct function. So, if you want to convert 2 into octal, you'd write oct2, and it will return the octal representation. Then we have converting a number into binary, which is fundamental in digital systems. Python provides the bin function for this. Calling bin1 will give you the binary equivalent. Moving on, we also have functions for converting strings into decimal integers, which is often necessary when processing user input or data read from files. The int function is used here, where you pass the string and specify the base if it's not decimal. For example, int 101(2) converts the binary string 101 into its decimal form, which is 5. And of course, type conversion or coercion in Python is straightforward. You just use parentheses like int num to convert a variable to an integer. This is a key concept because understanding how to switch between data types is essential for effective programming. Overall, mastering these conversion functions is crucial for handling various data formats and ensuring your programs work seamlessly across different systems and data sources. All right, let's take a look at this example. We have a equals 10 and b equals 20. Then, the line says if it is less than b, print hello. This is a simple way to see how Boolean values work in programming. The key idea here is that the condition a b evaluates to true because 10 is indeed less than 20. When that happens, the code inside the if statement runs and prints hello. Now, what's really important to understand is that Boolean values are basically just true or false. In programming, true is often represented as 1 and false as 0. And interestingly, even an empty string like is considered false. This example ties into the bigger picture of understanding how logic works in code. Being able to evaluate conditions like this allows us to control the flow of our programs and make decisions based on different scenarios. So, mastering Boolean values is fundamental because it lays the groundwork for more complex decision-making in programming. All right, let's talk about sequences in Python. A sequence is basically a group of elements or items that are ordered in a specific way. When we think about sequences, there are 6 main types to keep in mind. First, we have the range, which generates a sequence of numbers. Then, there's the byte array, which is a mutable sequence of bytes. Next, we have the tuple, an immutable collection of items. Moving on, the bytes type represents an immutable sequence of bytes. We also have the list, which is a mutable collection that we can change after creating. Lastly, the str type, which is a sequence of characters, essentially are strings. These sequence types are fundamental because they help us organize and manipulate collections of data efficiently in Python. Understanding these different types allows us to choose the right one for our specific needs and makes our programming more effective. And that brings us to slide 58, where we wrap up our discussion on data types with strings. Here, I want to emphasize that strings are fundamental in programming because they allow us to work with text data. As you can see, the string welcome is a simple example, and it shows how strings are enclosed in quotes, either single or double quotes. This is important because it helps the compiler or interpreter distinguish between code and text. Remember, whether you choose single or double quotes, consistency is key. The main takeaway is that strings are versatile and essential for handling all sorts of textual information in your programs, tying together the overall theme of understanding data types and their role in coding effectively.